In this video, I would like to show you the difference between overdrive, distortion, fuzz, uh, and the difference between the effects of a pre-amplifier and a power amplifier on your signal. And in order to demonstrate what each of the effects does, I now have a signal generator running here, which creates a sine wave of 440 with a frequency of 440 hertz, and this sine wave is currently displayed on a software scope. You can see the sine wave here. So that is the input to our the input signal to our effects units. And the first effects unit I want to demonstrate is an overdrive unit. And I will just enable the effects unit now. And at the first glance, it just looks like it has reduced the signal amplitude. You can see the signal still looks pretty much like a sinusoid, but the amplitude is now reduced. Now, an overdrive effect usually has several parameters that you can configure, such as gain, drive, and level. And when you reduce the gain, basically the signal amplitude gets smaller. When you increase the gain, of course the signal amplitude will get larger, but you will also notice that the signal begins to distort. So the higher the amplitude gets, or the more gain, the more amplification the overdrive effects unit has, the less linear it will react to the input signal. So you can see that the signal is basically extended in this area. The sinusoid has a lower slope at the zero crossing, but it goes higher. It doesn't flatten off like this. And as we continue to increase the gain, you will see that this effect gets more and more pronounced. So the slope of the signal through the zero crossing will get steeper and steeper, and the signal will get more and more squashed onto the basically the positive and negative supply voltage, which create a limit of how far the output amplitude of the effects unit can go. And as we continue to increase the gain, the signal through the zero crossing will get steeper and steeper, and the signal will get more and more squashed onto the basically the limit, the supply voltage of the effects unit. But the signal will always keep the characteristics of symmetry. So the negative half wave will look the same as the positive half wave. It will be as wide, and it will also be as high as the other. The signal is basically point symmetric through the origin. If we feed a sine wave into it, which is also point symmetric through the origin, and it will remain soft clipped, so the edges of the output waveform will be rounded and smooth. Now we have increased the gain to a pretty high value. It's at 30 decibels now. And now what I want to do is well, we have two more parameters that we can adjust. The first is the level parameter, and when we reduce the level parameter, you will see that basically only the output signal will reduce in amplitude or increase in amplitude. But it will do nothing to the shape of the signal. If we reduce the gain, say to 10 decibels, and then decrease the level, the shape of the signal will remain as it is, and only the amplitude will move up and down, but back to a gain of 30 decibels. And the level control will only scale the output signal up and down. Now we have one other control on our effects unit, and this is the drive control. And both the gain and the drive control control the amount of distortion that will happen, but they both have different effects, and you will see this. The gain, remember, the gain is now currently at a pretty high value. It's at 30 decibels, and when you will probably remember what happened as we increased the gain. So, or I can demonstrate this again. If we reduce the gain, this is how the signal behaves. Okay. So it gets less squashed towards the supply voltage, and it will get less. The slope through the origin will also decrease. Now we have the gain up again at 30 decibels, and now we will decrease the drive value instead. And this is what happens to the signal. So you will notice the signal will no longer clip that hard against the supply voltage. The clipping will get softer, but the slope through the origin will remain pretty high. So it's a different effect that the drive control has on the signal. The effect of the drive control on the signal is different from the effect on of the gain control on the signal. And if we move the drive control all the way down, we will basically have a clean signal again. So this is what the drive control does to the signal. Now I will put the overdrive effect in bypass mode again, so we will have a sine wave again, and I will now, instead of an overdrive effect, I will kick in a distortion effect. And we now basically see that nothing happened to the signal, which is because the distortion effect is currently set to a gain of 0 decibels. And of course I can decrease the gain, which will simply reduce our signal in amplitude, but I can also increase the gain. And as I increase the gain, you will see what happens. This, as with the overdrive effect, the slope of the signal through the origin will increase as the gain is increased. And well, the gain basically provides an amplification of the signal. So the input amplitude has to change less, or given with a given change of the input amplitude, the output amplitude will change more if the higher the gain value is, and the output voltage will only get to a certain point when where it hits basically the supply voltage, and then it can't increase anymore. So it will just remain constant until it drops back below the supply voltage. And the more we increase the gain value, the of course the stronger the clipping will be. And we're now at 30 decibels, and we have basically turned our sine signal more or less into a square wave. And the effects unit also has a level control, and as I move the level control down, as with the overdrive effect, the output signal will only be reduced and in signal amplitude. And if I move the gain value down, of course the clipping will get less, and of course also with less clipping I can then adjust the signal amplitude with the level control. Okay, so that's basically what a distortion effect does. And last but not least, we have a fuzz effect here. And when we enable the fuzz effect, you will see that basically a piece of the waveform is clipped, but it's just on one side. It's asymmetric. And now we also have a gain control on our fuzz unit, and if we increase the gain, as with our other units, the slope of the signal through the origin will increase, and the signal will get clipped both on the positive and on the negative side. And the more we increase the gain, the steeper the slope of the signal will get through the origin, and the more clipped it will be. Now, the clipping that the fuzzer applies to the signal is asymmetric, so the positive and negative wave they don't have the same length, even though remember the input signal to our fuzz unit is this, which is completely symmetrical through the origin. However, when you count the divisions of the length of the positive and the negative half wave in divisions, you will see that we have a positive half wave that is 4 divisions wide, and we have a negative half wave that is a bit more than 5 divisions wide. So the signal is not symmetrically clipped, it's asymmetrically clipped. And this is because the fuzzer applies a bias voltage to the signal before clipping it. And we can also adjust this bias voltage. We can move it more towards a positive bias. And then we will see that the length of the positive half wave, or the duration of the positive half wave in time, is reduced even more, and the length of the negative half wave is increased. So we now have a quite short positive half wave and a quite long negative half wave, and the positive half wave has a higher amplitude than the negative half wave. And of course we can also change the polarity of the bias voltage, so we will now decrease the bias, and as we move the bias through the 0 point, we will see that the clipping is now symmetrical. So it's basically the same as with the distortion unit, but we can also go negative on the bias. And then we will see, of course, that the positive half wave is now long and low, and the negative half wave is high and short. Okay, so it's just the other way around. Now, to get a better understanding of how this fuzz unit actually works, we will change the bias to 0 again, and now we will move. We will reduce the fuzz control. We will keep the gain high, but we will reduce the fuzz control. And the fuzz control on the fuzzer is basically the same as the drive control on the overdrive unit. And if we reduce the fuzz control, we can see that the clipping will get softer. So we can see more of the original input waveform. It doesn't all get squashed to the supply anymore. And we can reduce the fuzz value down to 0. Then we will have a clean signal. And now we will just slightly move the fuzz value up. So we, or maybe a bit more so that you can see it better. Well, okay. So now we have pretty much we have a pretty large region where the input signal is passed on linearly, and we only have this small discontinuity or nonlinear region in our input signal. Now what I will do now is I will move the bias control up and down, and then of course you will see that this nonlinear region will move up and down our input waveform. So I will move the bias upwards towards a positive value. And I will now, you will now see that one side of the signal is squashed onto the supply voltage. Therefore, I will reduce the signal amplitude from our function generator a bit. Okay, and I will continue to move the bias towards the positive direction. Okay. And now I will move it back to the negative direction. So basically the bias controls which region of the input waveform is amplified and distorted and passed on in a nonlinear way by the fuzz unit. And well, this, if I now increase the fuzz value again, of course the signal will get squashed to the positive and negative supply voltage again. And therefore you now have this basically pulse width modulated waveform here. Okay. So that's basically what a fuzz unit does. Now I will reduce the fuzz parameter again. So okay, what I will show you now is if I reduce the input amplitude to the fuzz unit, of course if this bias voltage were a constant voltage that was applied to or added to the input signal before it is passed through the nonlinear amplifier circuit in the fuzz, then of course there would be a point where the amplitude of the input signal is no longer large enough to reach this nonlinear region. And then the fuzz would basically clean up as the input no longer passes through this nonlinear region in the fuzz's transfer function. However, this is not the case when the input amplitude to the fuzz is reduced. Like, say, if you plug a string on a guitar, the oscillation will be a damped oscillation, so it will decay in time exponentially. Then, of course, there will be a point where the amplitude of the input signal will be will drop below this this nonlinear region in the transfer function of the fuzz, and then the output of the fuzz would suddenly clean up. It would no longer distort. However, this is not what actually happens. If the input amplitude to the fuzz is reduced, the bias voltage moves downwards along with it, so that this nonlinear region basically moves moves closer to the zero line as the amplitude of the input signal is reduced. And therefore the input signal will always cross through this nonlinear region. I will now demonstrate this to you by reducing the output amplitude of the signal generator. And as you will see, the signal that is passed on more or less linearly by the fuzz is reduced and drops down, but this nonlinear region is still crossed by the input signal. And of course, the change in voltage that occurs across this nonlinear region is now lower, because the amount of gain that the fuzz applies, even though it's pretty large, is still finite. So that you will see a lower slope of the signal, or a slower change in voltage here. Okay. Now, one last thing I want to show you is the following. I will now kick in the overdrive effect again with pretty high gain setting and maximum drive. And what I will now do is I will increase the frequency of the input signal, and this will move. This will reduce the spacing between these zero crossings, so the waveform will oscillate faster. But what I want you to notice is that even when the frequency of the signal is increased, the basic shape of the signal remains the same. So we will always have this soft clipped waveform and these rounded edges, and then the signal that flattens off like this. So I will now increase the frequency from the signal generator. And you will see that the basic characteristics of the signal remain the same. They're just moved closer together in the time domain. Okay, but the basic shape of the signal always remains the same if we change the input frequency to our overdrive circuit. And the other circuits will more or less behave the same. Of course, there will be a slight frequency dependency in each circuit, but it is not the main component or the main purpose of a pre-amplifier or a distortion circuit to show strong frequency-dependent behavior. So these circuits more or less only operate on the amplitude of a signal. They basically map each point in time, each voltage value through a sort of a nonlinear function, and that's basically the output signal from the circuit. On the other hand, I will now set the frequency back to 440 Hertz, where we started off. On the other hand, if we have a power amplifier circuit, it will show strong frequency-dependent behavior, and I will demonstrate this now. So I will kick in a power amplifier circuit, and this is basically the output of it. So the triggering is now not very regular because the signal has so many zero crossings. I don't know if we might get a more reliable trigger point somewhere around, yeah. Okay, now we have a more reliable triggering. And what I will now do is I will do the same as before. I will increase the frequency of the input signal. So the input signal now passes through both an overdrive preamplifier circuit and a specific power amplifier circuit. And what I will do now is I will increase the frequency of the input signal, and then you will see that unlike with the previous example where we only had a preamplifier circuit or an overdrive effect enabled, it will not be the case that this the signal period is simply reduced and the signal is squashed together and this so that these peaks are spaced more closely, but the principal shape of the signal remains the same. No, in this case, the behavior of the power amplifier circuit is strongly dependent on the frequency of the signal that is going into it. So as we change the signal frequency, we will see that the waveform that appears on the output of the power amplifier circuit will more or less change entirely. So I will now do the same as before. The only thing I will do is increase the frequency of the signal from the function generator. I will change no other parameters apart from the frequency of the signal that is output from the function generator. And as you can see, as I increase the frequency of the signal that is coming from the function generator, the output of the power amplifier circuit, and remember the signal is passed through both a nonlinear preamplifier circuit and the power amplifier circuit, the entire shape of the waveform that appears on the output of the power amplifier is changed. Okay. And I will now clean the signal back up. Okay. So yeah, I hope you enjoyed this video, and I hope it helped you get a better understanding of what the difference are between an overdrive, a distortion, and a fuzz effects unit, and what the effects are of a pre-amplifier and a power amplifier circuit on your signal. I will now demonstrate the effects of overdrive, distortion, and fuzz on a real guitar signal using go-dsp-guitar. Go-dsp-guitar has all these effects built in. It has an overdrive, a distortion, a fuzz effect, and of course it has power amplifier simulation. And I have configured the power amplifier simulation to simulate a British power amplifier with a relatively high filter order of 4096. So I will enable the power amplifier simulate, or let's just put it all in bypass mode, and I will show you how the clean guitar signal sounds like. And for this demonstration, I will just play an open or just play a D power chord, and the D power chord sounds like this. So this is what the input signal will be. I will now enable the power amplifier simulation for a British power amplifier, and I will enable the overdrive effects unit, and the overdrive is currently configured to a gain of 30 decibels and a drive value of 100%. And now we'll play the guitar again. Now I will reduce the gain value down to about, say, 15. Let's reduce it more towards 10 decibels. Now I will turn the gain up again, and I will decrease the drive value instead. I will first decrease it down from a value of 100 to a value of 50. And now I will reduce it further to a value of 10. Okay, now I will put the overdrive effect in bypass mode and enable the distortion effect instead. Again, this is set to a gain value of 30 decibels. Now I will reduce the gain value down to about 10 or say 15. Now reduce it further. And increase it again. Okay, so this was the distortion effect. Now we'll move on to the fuzz effect. And the fuzz currently has a gain of 30 decibels, a fuzz of 100, and a bias of 50. Now we'll turn the gain up and reduce the fuzz value instead. And now I will move the fuzz value back up to 100. And now I will shift the bias around. So the bias is currently at 50. I will now set it to 0, so no bias at all. And I will move the bias into the positive direction. So that was a demonstration of the overdrive, distortion, and fuzz effects unit, and I hope you enjoyed this video, and see you next time. Thanks a lot for watching this video.